Okay. This is Dr. Osman Hassan. I'm going to solve the quiz one that we wrote about 2 months ago. I've already sent the solution to the course rep, and I hope by now it has been distributed to you. But I'm going to solve the solution, and I'm going to be uploading this video on YouTube so that you can have access to the solution. This will go a long way to help you prepare for the final examination. I've solved other quizzes that I've done with other programs. For example, I've solved quiz 1 for MA, meaning mathematical students, and then quiz 1 also for information system students. I've uploaded both of them on YouTube, so you can search for those videos as well, because those videos have calculated some of the questions using different methods. So this will help you understand all the different methods that we have done. That is starting from chapter 1 to chapter 4. So the method that we have looked through, and this solution that I'm going to be providing, I'm going to be using for the circuit problems, meaning for question 2 and question 3. I'm going to solve question 2 using nodal analysis, meaning, right? Then question 3, I'll be using Thevenin's theorem to solve for question 3. So let's get started. Now I'm starting with question 1. So I have here question 1. Question 1. Question 1 here. Question 1. In a particular household, 9 light bulbs of 50 watt each are used on average 35 hours each, while an electric cooker of 200 watts is used on average 25 hours each. Determine the total energy used by the household. So we are talking about a household, in that case a particular household. So when it comes to household, the meter readings that we have, right? The meter readings are in kilowatt hours. So meter household. Household meters are in kilowatt hours. So that's the unit. So if you were to go and look at the meters that you have at your various houses, so if you were to go and look at it, then you look at very well, you realize that the readings there are expressed in kilowatt hours. That's the unit hours. So with this in mind, we are going to use that notion to solve for question 1. And then we are asked to find the total energy used by the household. That's A. And then B, find the total cost of electricity if 1 unit of electricity costs 75 Ghana pesos. So first, let's start with question 1A. So I have 1A here. So if you have in a household, you have night light bulbs of 50 watt each. So meaning I have, let's say, 1 light bulb is going to be 50 watts. Okay, now we have been told we have 9 of them, so I have 9 here. I have 9 light bulbs, so that means 9 light bulbs I'm going to get. Also, I'm going to get the total watts or the total power to be 9 times 50, which is going to be equals to, so this time this will simply be what, 450 watts. Okay, so we have 450 watts. So we have 450 watt for this question. So we have 450 watt. Now we continue with this question. And now, so we have 9 light bulbs of 50 watt each are used on average 5 hours each. So before we do this, we can calculate the energy. So meaning you can see that we are giving the 9 light bulbs are being used on average 35 hours each. So we can calculate the energy, right? So we can calculate the energy here. So energy, which is going to be equals to, E here will be equals to power times what? Time. Okay, so energy is the ability to do work. So meaning work done is a form of energy. So you get power being equals to energy over time, then you multiply power by time, then you get energy. So energy will be equals to this. So with this, I can now calculate the energy consumed by the 9 light bulbs. So energy consumed by the light bulbs. And we are being stated here that each of these light bulbs are used on average 5 hours. So this simply means that I can just multiply the power, which is 450 watts, times what? The time, which is 35 hours. So we get the energy of the light bulbs be equals to 450 times 350, and when you multiply this, you get 15750 watt hour. Okay, see a watt hour in the sense that because the unit for what, for power is watt, and then this is watt in hours, the time is hour, so watt hour, so you get watt hour. Okay, now once you've gotten this, remember I said the units should be expressed in what, when you come to the metering, expressed in kilowatt hours, right? So it's been expressed in kilowatt hours. So I'm going to change this to kilowatt hour. So this to kilowatt hours is going to be so in terms of kilo, that will give me 15.750, right? Kilowatts hours. So we get this. So now we continue with the question. While an electric cooker of 200 watts is used on average 25 hours each. So we are going to calculate the energy consumed by the electric cooker. So energy energy consumed. Okay, let me do it this way. Energy consumed by the electric cooker here. Again, it's going to be what? The power, right, of the electric cooker times what? The time. Okay, so meaning energy consumed by the electric cooker is going to be equals to the power, which is given the question as 200 watts. So I take 200 times time, and the time here is 25 hours. So I have 25 hours, 25 here. So we multiply 200 by 25. We get here, meaning you get 0, 0, right? 25 times this, then you get 50. So you get 5,000 watt hours. So we change this to kilowatt hours, so that we get the energy consumed by the electric cooker is going to be equals to 5 kilowatt hours. So we've gotten both energies consumed by the light bulbs and then the electric cooker. Now we are in, if you look at question 1a again, you have to determine the total energy consumed by the household. So the total energy consumed here is going to be total energy is going to be the energy consumed by the light bulbs plus what? The energy consumed by the electric cooker. So we have this. So this will give us the total energy to be equals to, we have here to be 15.75 plus 5 equals to, so if I have 15.75 plus 5, that will give us 20.75 kilowatt hours. So this is for 1A. Now let's go to 1B. Question 1B. Question 1B, you have to find the total cost of electricity if 1 unit of electricity costs 75 Ghana pesos. Right, 75 Ghana pesos. The unit, when it comes to the unit of electricity or the unit cost of electricity, is a way to inform you how to the price of what the energy that you've consumed is going to be calculated. So if, let's say, you've consumed 20.75 kilowatt of energy, now we are trying to find the price, how much you are supposed to pay for that energy you've consumed, right? For the energy that is being consumed by the household in this case. So we are given 1 unit of electricity is going to cost 75 Ghana pesos. A unit of electricity simply also means that simple means 1 kilowatt hour. Okay, so when you talk about a unit cost of electricity, meaning we are referring to what the cost of 1 kilowatt hour. So that means that 1 kilowatt hour of energy consumed is going to be 75 Ghana pesos. 75 Ghana pesos. So the household consumes what? 20.75 kilowatt hours of energy. So meaning that the cost of energy which is being consumed is going to be equals to 20.75 times 75 Ghana pesos. And that will give us $1,556.25 Ghana pesos. So with this, we are going to change this to what? To Ghana cedi, right? So to convert from Ghana pesos to Ghana cedi, what we are going to do is just that we are going to just divide the amount given in Ghana pesos by 100. So when you divide this by 100, we get 15.5625 15.5625 Ghana cedis. So we can write the total cost of electricity for the household. Total cost of electricity is going to be equals to 15.56 Ghana pesos. So that is for question 1. Let's move to question 2. So I have question 2 here. Question 2, calculate the currents in figure 1. So this is our figure 1. You have to find the currents in this circuit diagram. Okay? So meaning what that means is just trying to say that you look at the circuit and you try to first assign current to each branch and then try and find the current in each branch. That will give us a current. And I'm going to be solving this question 2 by using nodal analysis method. So we have here nodal analysis method, right? Of nodal analysis method. So in using nodal analysis method, First, I'm going to sketch the circuit diagram again and then indicate the currents in each branch. Then the next step will be to apply Kirchhoff's current law at each node, and then write the Kirchhoff's current law for the circuit diagram. Then we solve for the voltage. Then after that we try and get the current. So first, assigning current to each branch, applying Kirchhoff voltage current law at a node, writing the equation, and then solving for the voltage, and then later we solve for the current. So we have here 60 volts. Then we have 22 ohms here. Then I have 4 ohms. Then we have, this is 6 ohms rather. Here is 8. I have here to be 8 ohms. 8 ohms rather. Then here is rather 4 ohms. Then I have here to be 5 ohms. And then the next branch I have only 10 ohms. So this is the circuit diagram. So I'm going to indicate the current, right? So with this circuit diagram, if you look here, have current, can assign current to each branch. So I have 2 branches. One is here, this is a branch, another one is here, and another one. 2 or 3 branches I'm assigning current. So the first branch, I'm going to label that one as what? I1. Okay. And then the second branch, we label this I2. And then the third branch, I3. So you can see that I've indicated also the direction of the current, because I have the voltage source here, which is what? We have negative, positive. The shorter terminal is the negative and the longer one is a positive. So I'm taking the current to be flowing from what? Negative terminal to the positive. So we have this direction, and then when it comes here, we have a node, right? Because we have a junction where 2 or more elements are meeting. So this becomes my node. So I can label here node A. Have node A here. Then you can see that I have I2, I3. They are all both leaving the node. So I've indicated this. Now the next thing will now be to apply Kirchhoff's current law to this. So we apply Kirchhoff's current law to this. So this is node A, so meaning Kirchhoff current law at node A. This is at node A. So you can see at this node A, we look at the currents entering and the current leaving. So the sum of current entries will equal the sum of current leaving. So you can see that I have I1 is entering the node A. I1 is entering node A. And then I2 and I3 are leaving, right? I2 and I3 are leaving. So I can write this, that I1 is going to be equals to I2 plus I3. So after this, I'm going to now indicate the voltage at node A, right? So this will be labeled as VA. The voltage at node A is what? VA. Now I can write the current that I have in terms of what? The voltage here, which is VA. Then when it comes to the bottom node here, let's say we label at node B, we are going to ground that, right? We ground it, and then the voltage at node B here, because it's been grounded, is going to be 0. Okay, it's going to be 0. So we are going to now have node A. We express the current here in terms of what? Node A, meaning in terms of what? VA. I have here to be so I'm going to write this straightforward, right? So we are going to write I1, for example. If I have I1, this is my I1, is here. You can see that in this branch of I1, I have two resistors, 2 ohms and 5 ohms, right? Because this one current is going to be going through them, which is I1. So meaning 2 ohms and then 5 amps are in series. So when it comes to writing the current, right, in terms of the voltage and then the resistance, we are just going to indicate here I1, which is going to be equals to I1 here will give me, because here we are starting from what? 60 ohms. The current is flowing from 60 ohms to what? Let's say here's our node A, meaning VA. So we take what? Where the current is starting from is going to be the higher voltage, minus where the current will arise at the node where it's going to actually be what? The lower voltage. Right? So we take the difference. So I'm going to write 60 minus VA over the resistance, right? The sum of resistances in what? In that particular branch. So I have 2 ohms and 5 ohms, so it's going to be what? 2 plus 5 here. Then I'm going to do the same for what? The same for I2. I2 is here. This is our I2. You can see I2, the current is starting from what? VA, right? So I'm going to take VA, and it's going to arrive at what? Node B, which is mean the voltage here is what? VB. But remember, this is being grounded, so that becomes what? VA minus VB over the sum of resistors, which are what? In this branch, right? So you can have 8 and what? 4. So I have 8 here plus 4. Then we go for the last one, which is I3. I3 here, if we look well, you can see that I3, again, the current is originating from what? VA. So we take VA minus, again, then the current will come the whole way toward node VB here, meaning node B, right? And the voltage there is VB. We get VA, again, minus what? VB, all over what? The resistors in what? The third branch. So we have only one resistor there, which is 10 ohms. So we have this. So if we are going to simplify this, and we are going to get 60 minus VA over 7 here. Remember, VB is grounded, so that place is 0. So we get VA over 8 plus 4, that will be what, 12. Then we have here again VB is here, it's 0, it's been grounded, so we get VA over 10. Now if we were to solve this, you can solve this by multiplying by the common denominator, right? I mean the LCM. If we were to do so, you realize that you can, when you multiply by this, or you solve this, or try to simplify this further, you are going to get, at the end of the day, 7,200. What that means is that you can actually multiply both sides by 7 times 12 times 10. That means you can multiply both sides by 840, here by 840, and this one too by 840. Okay. So if you were to do so, you are going to get this part here to be 7,200 minus 120 VA, which is going to be 70 VA plus 84 VA. Then you simplify, then you get, then you send the VAT across the equal sign, I mean the minus 120 across the equal sign, and then that will give us 7,200 will be equals to, so when you send this become plus, and then you add 70 VA plus 84 plus 120, you are going to get 274 VA. Divide both sides by 274, that will give us 26.277 volts. Okay, so we get this answer here as the voltage at what? Node A. Now we are asked to find the current, so now let's get the current. So we can write here I1 is going to be equals to, from the equation that we wrote earlier, see that I1 is equals to what? 60 minus VA over 2 plus 5. So I can just write here I1 here equals 60 minus VA. Our VA is now 26.277 over 7, which is going to give us 4.818 volts. So we get this 4.818. Sorry, here should be 4. The unit is supposed to be amps. Okay, amps rather. Okay. Now we try and solve. So let's solve for now I2. I2 is also going to be equals to, it's already here. I2 is equals to VA minus VB over what? 8 plus 12, which is VB is 0, so you get 26.277 over 12. This will give us 1 219 amps. And then the last one, which is what I3 equals to, again we come to this part, we have our I3 being equals to this. So you have VA minus VB, so that is just going to VA over 10. So we get here to be VA, and EA is 26.27 divided by 10, so that would just be 2 point. So that is just going to be 2.628 amps. So we have this. So we've got in I2 and then I3. So these are going to be the current in the circuit. Now let's move to question. Let's move to question 3. Question 3. I'm going to solve question 3 using Thevenin's theorem, right? So we have Thevenin's theorem here. We have Thevenin's theorem. We are going to use Thevenin's theorem. So I have Thevenin's theorem here. Okay. Now, using Thevenin's theorem, we have to state the theorem or try and understand what the theorem entails. Thevenin's theorem is just saying that if you have a circuit diagram, no matter how complex that circuit diagram, you can simplify that circuit diagram to simply what you can reduce or simplify that circuit diagram to just a voltage source, right, in series, voltage source in series with what, a resistor, right? So we call this voltage source VTH, which is Thevenin's voltage, and the resistor, we label it as what, or we call it Thevenin's what, resistance. So if you have any complex circuit diagram, you can convert it to this form. This is what we refer to as what? We call this Thevenin's equivalent circuit, right? Equivalent circuit, right? So remember, the part that we are going to be converting is going to be what, then and load part, right? Then and load part of the circuit. So with your circuit diagram, you divide into two, the load part and then unload part. Now we go to what, question 3, right? Question 3. Now with question 3, find the power dissipated by the what? The 5 ohms resistor in figure 2. So we have our figure 2 here, so figure 2, and we have 5 ohms here. So 5 ohms. We have to find the power, right? Meaning power P here is going to equal to going to be equal to the current which is passing through this, right, times the what, its resistance, which is 5 ohms. So this is going to be the power. So we have to find this power dissipated. This means that first I have to try and get the current if I'm to find the power. So let's try and find a way of solving for the current. So the current that is passing through the 5 ohms resistor. Here, because we are using the Thevenin's theorem, since we are interested in the current that is passing through the 5 ohms resistor, meaning the 5 ohms resistor becomes our load, right? It's going to become our load. So that means that I can sketch the same circuit diagram, then divide it into two, whereby I have the load and then the unload part. So I can sketch this. We can go into sketch circuit diagram again. Here I have 70 volts, and I have a resistor. I have another voltage here which is 50. Then we have a resistor here, then another one. So here the resistance is 6 ohms. Here I have 4 ohms. Here we have 3 ohms, and then here is 5 ohms. Okay. Since we're interested in the current that is passing through 5 ohms, so we are interested in this current which is passing through this. This becomes our load, so meaning the load here becomes 5 ohms. Okay, so we are interested in the current which is passing through with the 5 ohms, so that becomes our load current. Now we are now going to divide our circuit diagram into two. So I have now the load which is 5 ohms. Then I have here, I'll indicate terminal here. So here terminal A and terminal B. So this is the load part, and I have here to be what? The unload part. Okay. So in applying Thevenin's theorem, the no-load part here is the part I'm going to convert, right? Is the part I'm going to convert to this, right? We are going to convert this to this. Is the part that we are going to convert to just a simple voltage in series with what? A resistor. So in trying to convert this, first we are going to isolate the load, meaning remove the load from the circuit diagram. We first isolate the load. The reason why we have to do that is because to get the VTH, right, I have to try and get the Thevenin's equivalent parameters, which is VTH, right, and then RTH. To get, for example, VTH, VTH is simply going to be the open loop circuit, right? So meaning you remove the load and then you look through to find the open loop circuits. That open loop circuit becomes the Thevenin's equivalent voltage, or Thevenin's voltage. So I'm going to remove the load. So I'm going to sketch the same circuit diagram again, but without the load, which is 5 ohms. So we have this. Let me use different color. Six ohms here, 4 ohms. Then we have here to be 60 volts. Now here to be what? 50 volts. we have this, and I'm going to have my 3 ohms. Okay, but now I've removed the 5 ohms, which is the load. So once we've removed it, this place here, we indicate positive and negative here. This open circuit, right? This becomes our open. So the voltage across this open circuit is what we call what? VOC, meaning that's the open circuit voltage. And VTH is going to be equal to what? The open circuit voltage. So I mean I have to calculate for the open circuit voltage. Once I've gotten that, that becomes what? My VTH. Now in getting this open circuit voltage, we are going to look through, right? So that means here you look at this, and when you are looking through, so when you look through this, right, you are going to see that the open circuit voltage, as we indicated, because here is open, right, there's not going to be any current that will pass here. So we just have this, you're looking at this place here, so you indicate here it's also going to be from here to that. It's just going to be equals to our open loop circuit, right? Now once we've done this, we can try and then find the open loop circuit, right? And if we indicate the nodes, right, at this point, right, we can indicate the nodes here. So I'm going to indicate this is node what? A, and then I have here node B, right? And I'm going to solve this using because this part here I'm interested in open loop voltage, so I can solve this by simply saying that the voltage at node here, VA, I'm going to learn VA here, and then the voltage here to be what? VB. So by doing this, I can ground again this part here, this node, because ground this node, so I can label VB to be 0 and have my VA. And then this open circuit voltage, this open loop circuit voltage can be equals to 1. There we are imagining that current is flowing through from what? The 70 volts. So if this current, so if I have current flowing through this, right, so the current is now flowing from what? VA to what? VB, right? So in that case, my VA is the high potential, so I'm going to write here to be VA, then it arrives at what? VB, which is what? The low potential. So I'm going to get VA minus VB. Once I've done this, I can now try and get what? VA, right? So I mean I have to solve for what? VA, yeah. Solve for VA. You can see that I can easily solve for VA. I can easily solve for VA here. VA, right? We can solve for VA by indicating the current. Like I said, let's say we indicate this one to be what? Current for this branch here to be I1. I1, and the current in this branch here to be 1. I2, maybe for this branch, let's say I3. But you can see that I3, because here is open, I3 here is going to be 0, right? So I3 here is 0. Now I can apply Kirchhoff voltage current law at node A. So if we were to do that, you can see that I have I1 is entering the node, right? And then I2 and I3 are leaving. So I can get here I2 equals to plus I3. Since this part is open, so I3 is 0. So here 0. So we get I1 to be equals to I2, right? So now I can go and write I1 in terms of voltage, meaning VA, and then the resistors in the first branch. I1 here will be equals to, starting from 70, right? Then it arrives at what? VA. So I have my noise VA here, all over what? The resistors in that branch. So we have only 6 ohms here, 6, which is going to be equals to, now my I2, right? I2 is going to be equals to, meaning VA, right? VA minus what? VB, right? Starting from what? VA arrives at what? VB. Then the over there, the resistor there, sorry, but you can see here we have what? VB. But before that we have here, let me just make this change here. You can see that we have another voltage here, right? Which is what? 50 volts, right? 50 volts. So you can see that because the current is moving from what? VA to what? Meaning it's going to arise, of course, up to VB, but VB is 0. But before that we have another voltage, which is 50 volts, right? So we can see that it's moving from here to what? 50 volt as well. So I can write here to be VA minus, can write VB, 50 minus VB, right? And VB, as we know, is going to be 0. This is 0. Then over what? The resistor, which is in that branch, we have only 4 ohms. So we get here to be 70 minus VA over 6, which is equals to VA minus 50 over 4. And when you solve this, and you can solve this by multiplying both sides, right, by 24 here, then what you are going to get, you are going to end up with what? 280 minus 4 VA is going to 6 VA minus 300. So you group like terms, right? So we take this across, right? Meaning you get 300 plus 280. That is going to give me 580. Then we send this one across, so we get 10 VA. So that means that VA is going to be simply going to be equals to 580 over 10, which is going to be 58 volts. So that is our VA. So this becomes a VA. Once I've gotten this VA, so we go back. Remember, I wrote earlier the open loops circuit will be into VA minus VB, right? So you can see here is 58, meaning minus VB, which is 0, so meaning the open loops voltage is going to be equals to 58 volts. and then we know VTH, the Thevenin's voltage is going to what? VOC, which is also going to 58 volts. So we've gotten the Thevenin's voltage to be 58 volts. Now let's get the other parameter, which is what? Thevenin's resistance, right? So we have to get this Thevenin's resistance, which is RTH. So I have my RTH, right? So we have to find RTH. Now, in solving for RTH, again, we go back to the circuit diagram, right? Circuit diagram. I have my load, and this is my non-load, right? The non-load part of the circuit diagram is this. So I come to this non-load part here, meaning with the load resistance being removed, then I'll look at this circuit diagram to get RTH. RTH here is going to be equal to the equivalent resistance when all independent sources are being turned off, right? So meaning RTH is going to be equal to the equivalent resistance, right, when all independent sources are turned off, right? So we go to the sources. So you can see that in the circuit diagram that I have here, then a load one here that I have here, I have two voltage sources, 70 volt and what, 50 volt. So I'm going to turn them off. And when it comes to turning off a voltage source, you simply connect a wire, right? You short circuit the voltage. What this just means is that you come to the same circuit diagram. So wherever I have my resistor here to be 6 ohms, I'm going to turn on, you just connect a wire, right? Then we come to the other one, which I have 4 ohms here, and I have the place for the 50 volts. I'm going to turn it off by connecting a wire. Then I connect this. Remember, I now maintain the 3 ohms here. So here's 3 ohms. So I maintain my 3 ohms. Okay. 3 ohms. Okay. You can see that with this circuit, now we have only resistors, right? So here we are just going to look at the arrangement of the resistors in this circuit, right? The arrangement of the, you can see that 6 ohms and 4 ohms are what? They are in parallel, right? Because they are connected end to end. This is connected end to end, right? And then after that, we have 3, they are in series with what? 3 ohms. So I can write here. So we can write RTH. Okay, we use a different color. RTH is going to be equals to the equivalent resistance for this circuit, which is going to be equals to 6 ohms, and then 4 ohms are in parallel, and then they are in series with 3 ohms, so you have 3 ohms. So this will give me, you decide per mean, I guess 6 times 4 over 1, 6 plus 4 plus 3. Okay, So 6 times 4 is going to 24 over 6 plus 4, which is 10. So I get 24 over 10 plus 3, which is going to be 2.4 plus 3. So RTH is going to be equals to 5.4 ohms, right? I have 5.4 ohms here for this. Now with this, we are going to now go back and solve for, we've now gotten our equivalent circuit. So I now have my VTH, right? And you're now having my VTH, which is equals to, I got it to be equals to 58, 58 volts. And I have my RTH to be equals to 5.4 ohms. So this is our equivalent circuit. Once we've indicated our equivalent circuit here, we connect the load, which is what? 5 ohms. Okay, connect this. Then we try and get the load current, which is IL. So this is going to give me So this is now just a simple circuit diagram. You can see that 5.4 ohms, and then the 5 ohms here are what? In series, right? These are in series. So if they are in series, I'm interested in the current. I'm going to write IL here, which is going to be equals to what? Meaning the voltage source, but now is VTH over 1. The sum of the resistors in series. I have RTH plus, they'll call this RL, right? The low resistance. So when you do this, you are going to get, so I have 58 divided by 5.4 plus 5. So now it's going to give me 58 divided by 10.4. So which is going to give me, okay, I'm going to get 5.577 amps. Now I've gotten the current, which is 5.577 amps. So the power now is just going to be equals to, what is that? It's going to be IL squared times the low resistance, which is going to be equals to 5.577 squared times 5. And that is going to give me 1.515 watts. So this becomes our answer for power. Okay, so like I said, I'll be uploading this on YouTube, so you are going to see the solution there.